In this video, we're going to talk about what's called a standard matrix for a linear transformation. So the question we're going to be trying to answer is, if we're given a linear transformation T that goes from Rn to Rm, how can we find a matrix A that corresponds to it? So A is the matrix that corresponds to the linear transformation T. So ultimately, what it is that we want is, when I plug in some vector x into T, I want the matrix A. I'm trying to find a matrix A that sort of does the same thing that T does. So when I multiply the matrix A by a vector x, I want that to be the same thing as plugging x into T. So I'm trying to figure out, well, what is this matrix A? Can I find a formula for it? So to do that, I want to begin with a definition. Okay, so the n by n identity matrix, the n by n identity matrix, which is denoted I sub n, is, and now let's write down a formula for this matrix. Okay, so I sub n is defined to be equal to, that's why I'm writing a colon in front of this equal sign, defined to be equal to. So the first column has a 1 at the top, and then everything underneath that is a 0. The next column has a 0 at the top, a 1 in the second spot, and then zeros below that. So what's happening here is we're forming a matrix that has 1s running along this diagonal and zeros everywhere else. So the very last column should have zeros everywhere, except for the very last entry is going to be a 1. Okay, so there are 1s on the diagonal and zeros everywhere else. Zeros everywhere else in this matrix. Okay, so why is this matrix called the identity matrix? Okay, so what I want to note is, if we take this matrix and we multiply it by a vector, it turns out we just get that same vector out. We get the vector x. So the identity matrix is sort of like the matrix version of multiplying by 1. When I multiply a vector x by the identity, it doesn't change it. Okay, to see why, let's just look at a simple example. Let's say I had the 3 by 3 identity matrix. So I have 1s on the diagonal of this 3 by 3, zeros everywhere else, and let's say I multiply by a vector x1, x2, and x3. And now we're pretty good at multiplying a matrix times a vector. So you could check that if we multiply this out, we're going to get x1, x2, x3. So you could either do this by, taking this first entry, letting that be the weight of the first column. So x1 times the first column, and then the second entry is x2 times the second column, 0, 1, 0, and then x3 times the third column, which is 0, 0, 1. So we could definitely do it like that. And that's one way to check why this is going to be x1, x2, x3. We could also multiply these using the row vector rule. Okay, so next I want to give another definition. So the columns of this identity matrix are special. They show up all the time. So we have a special way to label them. The first column we call E1. The second column we call E2. The last column we call E sub n. So we're going to see these labels a lot in this class. So this is the first time we're being introduced to them. Okay, so I want to note something else about these column vectors. So what I want to note is, I want to note that if we have a vector x with n entries, so x1, x2, so n entries, all the way up until xn. So a vector x with n entries. I can write it as a linear combination of e1 up until en. We sort of saw that up here. We had this vector x, and we wrote it as a linear combination of the columns of the identity matrix. So I'm going to use that same idea So this vector x is, just in the same way that I did up before, it's going to be x1 times the first column of the identity matrix, plus x2 times the second column of the identity matrix, plus dot dot dot, plus xn times the last column of that identity matrix, E sub n. And we could quickly check that, both sides of this are the same. It's really similar to what we did up here. It's really similar to that. Okay. So I just realigned the page a little bit so I could see the whole problem a little bit better. So remember, what I wanted was, I wanted to find this matrix A that corresponds to what T is. Okay, so in this last line that I have here, I know that the vector x equals this linear combination over here. So I want to get a feel for what T of x looks like. So let's take T of both sides in this equation. Okay, so let's take T of both sides. So doing that, on the left-hand side, I'll get T of the vector x. On the right-hand side, we'll get T of the linear combination x1 e1 plus x2 e2 plus dot 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 plus xn en. Okay, so I took T of both sides. And now the right-hand side, I can simplify. I can simplify using the fact that T is linear. Using the fact that T is linear, I can first split this up as T of the first vector plus T of the second vector, x2, e2, plus dot 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 plus T of the last vector, exn, en. So that's using the fact that my transformation, my function here is linear. And then there's another property of linear transformations, where if there's a constant inside of my function, I can pull it out to the front. So if I do that with all the constants, I'll get x1 in front times T of e1 plus x2 in front of T of e2 plus dot 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 plus the xn in front of T of e sub n. Okay, so now what I have is I have another linear combination of vectors, but the vectors are T of e1, T of e2, all the way up until T of en. And if I have a linear combination of vectors, I can write this as a matrix times a vector. This is going to be the matrix where the columns are those vectors, T of e1, T of e2, dot 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 until my last column, T of e sub n, multiplied by the vector where the entries are the weights of the linear combination. So those are x1, x2 up until xn. So x1, x2, dot 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 up until xn. Okay, so what we've done is we've rewritten T of x as a matrix times x. So this vector right here is just x. Okay, so what's the size of this matrix right here? Well, I know that it definitely has n columns. Sorry, so that's an x and an n. So how many rows does it have? So remember that T is a transformation that goes from Rn to Rm. That's what we were given. So that means when I plug in something like E sub n into T, the output has to live in here. It's got to be an element of Rm. This is in Rm. So that means this vector has m entries. So this matrix is going to have m rows because each of these vectors is m entries. Okay, so this is an m by n matrix. And that is actually the matrix that is associated with T. So let's state that as a definition. So if I'm given that T is a linear transformation from Rn to Rm, we say that the standard matrix that's associated to T is, I'm calling it A, and it's the matrix where the first column is T of E1, the second column is T of E2, all the way until the last column of that matrix is T of En. Okay, so we'll do some examples where we compute this matrix for a given T. But first I want to state a couple of things. So the first thing I want to state is a key fact, which is we constructed this matrix X so that T of X is the same thing as A times X for all X. for all vectors x that are in Rn. So the matrix A and this function t are sort of doing the same thing. When I plug x into t, and when I multiply A by x, they should always be the same. So the conclusion, why this is important for us is, anytime we have an m by n matrix, in fact, if I look at just all m by n matrices, I can think of any m by n matrix as being a linear transformation and vice versa. As being a linear transformation, t from Rn to Rm, and vice versa. So another way to say that is, m by n matrices are the same thing as linear transformations t that go from Rn to Rm. If I start off with a linear transformation that goes from Rn to Rm, I can put it into matrix form, like the formula for a standard matrix shows, and vice versa. If I start off with a matrix, I can write it as a linear transformation, like we saw in the last video. Alright, so let's do some examples. So example 2, let's find the standard matrix for this transformation t. So t goes from R3 to R3, and what it does is it projects points onto the xy plane. Okay, so how do we solve this? What is the solution? So I'm going to begin with the formula for the standard matrix. So I know the first column of the standard matrix is t of E1. The next column would be t of E2. But when do I stop? I stop depending on what the domain is. So I'm going to have 3 columns since the domain is R3. So that's how I know when to stop. Depends on what my domain is. If my domain was R4, I would go up until I would have 4 columns in my matrix. Okay, so I need to figure out what these column vectors are. So I need to know, for example, what t of E1 is. So let's use the geometry behind this transformation to figure that out. So what I'm going to do is I'm going to draw my x, y, z axes. So x, y, z axes. And then I'm going to draw the vector E1. So E1 is 1 unit in the x direction. So it's the vector 1, 0, 0. So that is E1. And I want to know what t of E1 is. What is t of E1 equal to? In other words, what happens to this vector, this blue vector, if I take the endpoint right here and I project that on to the xy plane? Well, this vector is already on the xy plane. So when I project it, nothing happens to it. It's just going to be the same thing. So t of E1 actually just equals itself. Okay, so that's kind of nice. So let's just write down the reason why. It's because E1 is already on the xy plane. So when we project it, it doesn't move at all. Okay, so now I know what this first column is going to be. It's just going to be the same thing as E1. So let's draw xy axes, xyz axes to figure out what happens to E2 and E3. So let me just go ahead and draw those in. So drawing them in, so x, y, and z. Alright, so now let's draw E2. So E2 is 1 unit in the y direction. So this would be E2. This is 0, 1, 0. That is the vector E2. So what is t of E2? What happens if I project this vector, which lies on the y-axis, if I project that onto the xy plane? Well, this vector is also on the xy plane already, so it doesn't change either. So when I project it, I just get the same thing. It doesn't go anywhere. Where it gets more interesting is when I talk about E3. So if we draw E3, E3 is 1 unit up in the z direction. So this is the vector 0, 0, 1. And that's E3. So E3 equals this vector right here. But what happens to that vector? What is t of E3? What is the projection of E3 when I project it down onto the xy plane? So this one is going to go somewhere. So here's the tip of E3. And if I project that down onto the xy plane, it's going to end up straight underneath down here at the origin. Okay, so when I project E3, it goes straight down and just becomes where the origin is, and that's 0, 0, 0. Okay. All right, so what do I do with this information now? So what this tells me is I'm actually ready to write down the columns of my matrix A. The first column is T of E1, and I know T of E1 just equaled E1, and that's 1, 0, 0. The second column was T of E2, and I know that T of E2 equaled E2 here, so that's 0, 1, 0. The third column is T of E3, and I know that T of E3 equals the 0 vector, so this is where it's different. T of E3 ended up being the 0 vector, and that is my standard matrix. That is the standard matrix that is associated with this transformation, with projecting points in R3 onto the xy plane. Okay, so let's do a reality check and see if we can understand why this matrix projects points onto the xy plane. Okay, reality check. So if I take this matrix A and I multiply it by a vector, does it project that vector onto the xy plane? So let's write out the matrix. So it's 1, 0, 0, 0, 1, 0, and then 0, 0, 0. Okay, and if I multiply that by some vector x in R3, x1, x2, x3, if I do this multiplication, what I'll get is, so if I do my row vector rule, so I would do the x1 times the 1, x2 times the 0, x3 times the 0, and that will give me x1 for the first entry. Sorry, let me rewrite the x1 back in there. I just wanted to erase those lines so they don't clutter my work. If I do the same thing for the next row, I will get x2 for this entry. For the third entry, I would have x1 times this 0, x2 times the next 0, x3 times the last 0, so I would get 0. Okay, so when I multiply my vector by A, I get x1, x2, 0. The third component is just becoming 0. If I were to draw a picture of that, so if I have my x, y, z axes, x, y, and z, and then I draw some arbitrary vector in R3. So let's say this is my vector x, and this is entries x1, x2, and x3. Okay, so think of like x1 is, some number of units in the x direction. x2 is some number of units in the y direction. So let me draw some dashed lines to help us visualize this. Okay, and then what does this vector look like? x1, x2, and 0. Well, what's happening is we're taking this tip, and it actually just goes straight down here. Because if I look at that point, it's got the same x coordinate, x1, same y coordinate, x2, but the z coordinate is now 0. If I draw that vector in, I get this, and that is x1, x2, 0. Okay, so my vector x did get projected down onto the xy plane. So we've just verified that the standard matrix that we were getting is actually projecting things onto the xy plane. Okay, so next, I want to state a conceptual observation and then do another example after that. So the observation is, if T is a linear transformation that goes from Rn to Rm, then to figure out what T is, all I need to know is what T of E1 is, what T of E2 is, all the way up until T of En. If I know all of these things, that lets me construct, that's enough to construct this matrix, this standard matrix. And that standard matrix perfectly describes what T does. So that's kind of cool that I just need to know what's happening with T of E1, T of E2, all the way up until T of En. Okay, so let's do another example, finding the standard matrix. So in this next example, let's suppose that T is a function that goes from R2 to R2, and this is a rotation by theta, so theta is some angle, counterclockwise about the origin. Okay, so this T is a linear transformation. So I've written here in blue that just as an exercise, you can convince yourself that T satisfies these two properties. So for example, property 1 says that when you look at T of alpha plus beta, that means, okay, if you have a vector and you're going to rotate it counterclockwise by alpha plus beta degrees, just all at once, that's the same thing as the right-hand side. The right-hand side, sorry, actually, let me correct myself there. I got to change some of this. So I misspoke a little bit. Let me fix this. So what this should say is it should say something like T of U plus V. And on the other side, it should say T of U plus T of V. And then over here, this should say T of C times U. And then equals C times T of U. So for example, and the reason why I'm changing it is because the things that I plug into T have to be things in R2. So they're not supposed to be angles, they're supposed to be vectors. So I need to write vectors here. So T of U plus V is talking about if you had two vectors and you add them together, and then you rotate that by theta. Well, that's the same thing as first rotating U by theta, counterclockwise, rotating V by theta counterclockwise, and then adding those vectors together. So I'd encourage you guys to think about that and convince yourself why that's the case. Okay, so let's find the standard matrix. So what is the solution to this? So my formula for the standard matrix is I have A equals, so the first column is going to be T of E1. And in this case, because my domain is R2, I know I'm going to have just two columns. So T of E1, and there's going to be a T of E2, and that's where I stop. Okay, so just like before, now I need to figure out, well, what is T of E1? What happens if I take E1 and I rotate it theta, an angle of theta counterclockwise? So I want to draw a picture to help me visualize this. So I'll draw my XY axes in this case. And then I'm going to draw the unit circle. I'm going to draw the unit circle because E1 lies on it. It goes right there. That's E1. E1 is the vector 1, 0. And E2 also lies on it. So E2 goes straight up. So E2 is 0, 1. And now let's rotate both of these vectors by theta, by an angle of theta. Okay, so if I do that, so let's say first I'm going to rotate E1. So if I rotate it by an angle of theta, then I get T of E1. That's what T of E1 represents. But if this is an angle of theta, I know based off of the unit circle that the x-coordinate is going to be cosine of theta. I know that the y-coordinate is going to be sine of theta. Another way I could see that is if I were to draw a perpendicular here. If I were to drop a perpendicular here and I were to redraw this triangle. This is theta. The hypotenuse, because it's a unit circle, is 1. So if I call this y and I call this x, I know that cosine of theta, for example, is going to be x over 1. So that means x equals cosine theta. So that's why this topmost entry is cosine theta. I could do something similar to get the y. Okay, so that's what T of E1 is. I know what this first column should be. So let's also rotate E2 by an angle of theta counterclockwise. So if I do that, and I do the same like right triangle thing. So I do the same right triangle thing. I know that this y, this vertical length, is going to be sine of theta. And by symmetry, that corresponds to this length right here. So this length is going to be sine of theta. Okay, so if I write down what T of E2 is now, the x component, so the x component of this vector corresponds to this length. But keep in mind that it's going to be negative. So it's going to be negative sine theta. Because just based on my picture, the x-coordinate here is negative. Okay, and then the y-coordinate, at least in my picture, is positive, and the y-coordinate corresponds to this length, which is the same thing as the horizontal length in the first vector. So it's cosine theta. So one of the things that you guys might be wondering is, wait, is this true? Like, even if my angle were bigger, like what if my angle rotated it this far? It turns out it is. So I'm not going to show in my picture that it's true for, angles larger than 90 degrees, but it turns out the same, it is true even there. And I could show it using some trig identities. Okay, so for our purposes, this is good enough, so I'm going to proceed. I'm going to write down the formula for A. So the first column is T of E1, which was cosine of theta, sine of theta. The second column was T of E2, which is negative sine theta for the first entry, and then cosine theta for the second entry. Okay, so that is my standard matrix right there. This matrix represents rotating a vector by an angle of theta counterclockwise through the origin. Okay, so what I want to note about this is if I were to take this matrix and multiply it by a vector, what that means is this should represent rotating x by an angle of theta counterclockwise. So I'm just going to write CCW to refer to counterclockwise around the origin. And that's pretty cool, I think. And I would encourage you guys to try it. So maybe play around, pick a value of theta, something simple. Pick a value for the vector x. Try multiplying this matrix by the vector x and see if what you get out is a vector that would correspond to rotating the vector x by theta counterclockwise.